Good morning, everyone. Sorry for the 3-minute delay it took me to get online. Zoom is moving really slowly today. Not only that, I started a video uploading from your Wednesday class. Excuse me, today is Thursday, so it's from your Tuesday class. That's finally going up right now. I was altering, editing the other videos and trying to get them up before putting this one up. So I started putting this one up actually about 5 till 8. So that gave me an hour and 35 minutes to get it done, but it's saying that it's still uploading. So that's kind of a bummer. It just takes a long time, evidently. But right now it's showing that I've got 9 more minutes left. So I suspect the video quality is going to be poor for the next 9 minutes or so. I apologize. I'd like to stop it, but I've wasted so much time already. I don't want to, completely have done it for nothing. Let's start off. Does anybody have any questions about course material so far or anything like that? I just decided in my 242 class that I'm moving your first online test to a week later instead of being due, I think on Tuesday. So I'm probably going to do the same. I'm planning on doing the same thing with yours. If it's due this Tuesday, I'm going to go ahead and make sure you guys have until a week after that to do test 1. So we'll just say that's done right now. That's when the due date is. If it's already been set on the syllabus as, 5-6 days from now, I'm going to move it a whole week back.
Professor.
Yes, Justin.
Do you know when? Do you know when you're gonna upload the Tuesday morning lecture? Because I missed class that day.
Yes, that's the one that's loading up right now. It should be done in.
Oh, okay.
Should be done in 8 minutes now. It's 92% of the way done.
Okay, thank you. Appreciate
Sorry
it.
about that being so delayed. I like to do them on the same day, but sometimes even if I do them immediately after class, I still don't get enough time. I can usually fit one lecture in between my last class and my first lab of the day. But like I said, this morning I started an hour and 35 minutes before class and it's still not done. So apologize for that.
And I have a couple of questions about the.
Go ahead, Silas.
I have a couple of questions about the homework. I'll wait till after, just because I don't want to take time of the class.
That's no problem. And you actually already had lab. I do have a class right after this one. It's only like 10 minutes, but if we can fit that in, that's great. If not, I did see your email this morning. I'm sorry for not seeing it until about 20 minutes ago.
No, that's fine, sir.
Anybody else? All right. Well, as far as chapter 2 goes,
I have a question.
Go ahead, Jonathan.
When do you plan on uploading the online test?
The practice test is already up. The online test is technically there. I just got to open it up. But like I said, I think I had it due either Monday for my Monday class or Tuesday for my Tuesday class. It's now going to be a week later. So normally I would say it would be opened on Thursday and due Monday or Tuesday. And that's fine. I could have done that, but I just don't like that. I'd rather you guys have a chance to ask me questions about chapter 2 before taking the chapter 2 test. So I'm definitely going to make it. I might even make the test available this weekend anyways, even though it's not due till the following.
Thank you.
No problem. Homework assignments, do the time limits matter? No, they're actually not time limits on the homeworks. They're giving you the average time that across the nation all the students have taken. You should look at that as a guide to whether you're being too persnickety. I'm sort of obsessive compulsive, so sometimes I spend a lot of time on problems that I shouldn't spend a lot of time. Like the publishers, when I work for like Norton or Prentice Hall or something like that, they tell me they're paying me $150 an hour, but it normally works out to about $15 an hour because I spend about 10 times as much time as they're expecting. So keep an eye on that just to see, hey, maybe I'm wasting too much time. I need to get faster. And the only way you're going to get faster is being more confident and working more problems. Anyone else?
Professor, is there a time limit on the online tests?
The tests, yes. The online tests always have a limit. It's usually on the order of 20 some minutes for 6 to 8 problems or something like that. Basically, I'm trying to give you enough time to where if there was exactly one problem that you couldn't remember how to do, you could possibly look it up and get a jogger of your memory and then do it. I find that I'm probably giving a little too much time even then, though, because that was my goal, but I'm seeing a lot of really high averages on the online tests. And then when we have a face-to-face test, where you've got all the time in the world, but you can't look up on the internet. People are doing a lot worse. So that's what I currently have. You've got an advantage on time. I just want you guys to focus on, if you can't solve, more than one of those problems on the homework without looking something up, then you're not really learning the material very well. So just keep that in mind. But yeah, that's the whole reason I set a time limit on it all. The practice tests are uploaded.
Okay.
They're supposed to, Ariel asked if the practice tests are uploaded. They're supposed to be, let me look right now. Maybe I'd unpublish the area where they're at. Let me let Liam in. I'm going to share my screen. I'm going to share, let's share this one. So you can see I got 5 minutes left. This isn't the screen I want to show you, but I got 5 minutes left for me uploading the video from Tuesday. I'm wanting actually this one, and now I'm going to go back over here to modules. Once this stops uploading practice tests, and let me see if then, wait. Why is it not even here? I do not know why the practice tests are not here. I copied them over before classes started and they're not even here. So I will fix that probably sometime today. Let me make a note of that too. So they will be up. I apologize. I thought they were up all this time. I will fix that. Sorry about that, folks. Okay, so it does appear that that practice test was not available. I apologize. We'll make that straight, but the good thing I'd already pushed your test back a week. That gives you a lot more time. Those practice tests are the best thing you can do. Once you've done your reading and your homework, you're in a pretty good space to understand the material pretty well. You can start doing those practice tests, and the more times you do it, the more different problems you see. And since I'm using more or less the same bank that I use for the practice test, I use that same bank to make my real test. There's a probability that you're going to see problems from the test on that practice test. And I guarantee that it's at least 80% of the points on the test. So I might make up 2 questions or 4 questions so that you get 2 to 4 questions that you haven't seen before. But the worst they could count against you is 20%. So yeah, it's crazy not to take practice tests. So do it over and over and over as often as you can. And try to get where you can solve them without looking stuff up. That's the goal. If you can consistently, get an 80, 85 without looking anything up, you're probably ready to roll on the test. All right. Any other questions? And then we'll move on. I've seen everybody's chat. I think I've hit everybody that's saying stuff. Yeah, so I just answered that, Linda. The homeworks are sort of, there are a couple easy, and then there are a couple that are kind of tight and difficult, hard problems, but that's not a real good experience level. In other words, they're very good because they show you the easy stuff. They're tutorials in some cases, so they actually walk you through how to do problems, and then they expose you to some of the harder problems. That's the way the homeworks are set up, but they're way too few. So they're excellent to prepare you to really take the practice test, to be honest with you. And then the practice test is the best way to study for the test. What your golden goal here is, though, in this course, probably more so than your knowledge of physics, unless you are actually going for physics or engineering, is your ability to learn to read material from a book and learn how to do things from that read material. That's sort of the gold standard of a collegian, someone who has completed college in a reputable way at a reputable institution. Normally they have a stamp on them that employers see, well, this person could probably take a white paper, read it, and then apply it. So that's sort of the gold standard of what you were trying to shoot for here. So keep that in mind. Anyone else? All right. So in chapter 2, I've already done all the derivations. The only equation I didn't give you was one that's true in very specific cases, specifically when gravitation, or excuse me, when the acceleration is a constant. But that's pretty much what we derive those equations from anyways. So the x equals 1/2 at squared plus v0t plus x0, that's only valid for an average acceleration, or more specifically, acceleration that's being a constant. Okay. Because even if you do an average acceleration, that equation might not work too nice, because the average acceleration just behaves normally when you're computing final and initial velocities. It doesn't do much regarding how far it's traveled. So the x equals 1/2 at squared plus v0t plus x0 equation. God, I feel so sorry for my interpreter trying to explain that. That equation is not that helpful when you have a changing acceleration. So keep that in mind. Changing acceleration is not really what we're trying to study here. The v squared equals v0 squared plus 2a times x minus x0. That is another equation that's made from acceleration being a constant. But it turns out if the acceleration really is a constant, then you can take the velocity at any 2 points and actually take the average of those, and that's another equation that can actually get you the average velocity is by adding 2 velocities at any point in time. But anyways, that's another equation that's sometimes used, but we never use it in the calculus-based physics problems. So I just want to let you know, you might see that like in a 201, 202 level textbook, which is the Giancolli's book, where it doesn't say for scientists and engineers on it. So I don't use that equation. There's no real need to use it. But anyways, these equations are good enough. The other thing that we got to cover in chapter 2 is basically reference frames. So you've probably noticed this to some extent before, but if you're standing on the side of the road, Portsmouth Boulevard or something like that, I actually grew up in P-Town, so that's my most experienced place, is riding my bike down the side of Portsmouth Boulevard. The speed limit there is say 35. I think it is, at least near Elmhurst, where I used to live. But the speed limit there is 35. If I'm standing still, I'm seeing these cars go by me at 35. And they might be going from my left to my right on the lane closest to me. In the farthest lane, they're going from my right to my left. So I naturally call the right the X direction and up the Y direction. And that's a perfectly valid frame. But if you happen to be standing on the other side of the street, you're probably going to call my left the positive X direction and my right the negative X direction. And that's okay too. That's the nature of physics, is we're allowed to see it from any angle, and our conclusions must still be right, independent of what coordinate system we use. That's ultimately how Einstein stated his general theory of relativity. So that's something that's big in physics, is you got to be able to do that. You got to be able to find the laws of physics independent of what reference frame you're using. Now, with me, I see these cars flying by at 35 miles per hour. And then if you're actually one of the people in the car, maybe you think straight ahead is the positive X direction, and that's good. That's a decent coordinate system. And up is still the Y direction. So we all agree on that one, all three of us. But the person riding in the car is actually saying, hey, there's Billy Younger on the side of the road going in the negative X direction. And in fact, they say I'm going negative 35 meters per second. In other words, the negative just gives the direction. The magnitude of the velocity being a vector quantity, magnitudes are always positive, always positive, always positive. Magnitudes are always positive. Okay, just something to keep in mind. Magnitudes are always positive. The negative in one dimension is just specifying the direction. So when I jump from my frame to the person's frame in the car, then basically my velocity was seen as the negative of their velocity. And that's just written like VAB, meaning the velocity of A with respect to B. So that's V sub A, B. That is equal to the negative of the velocity of B sub A. Let me write this in equation form so you'll understand what I'm saying. And especially for my translators. So one of the things I'm saying is that the velocity of object A, as seen by frame B, I'll put a vector symbol over it. We'll discuss the vector more later, but you just should recognize this is something that has magnitude and direction. That's equal to the negative of the velocity of frame B with respect to A. Okay. When you multiply a vector by a negative, you're just taking the vector that was pointing that way and turning it that way. If there was a number other than 1 here, then you'd either make it longer if it's greater than 1, or make it shorter if it's smaller than 1. That's all that happens with vectors. So what we're saying is the velocity of the person in the car with respect to Billy was 35 meters per second, or 35 miles per hour. But the velocity of Billy, as seen by the car, is negative 35 miles per hour. So that's one of the big things about reference frames is you got to keep that in track, because this is a fundamental idea that AB is equal to negative BA. The other thing is if I see a person riding by in that car, and let's say now it's a flatbed truck, okay, and I see someone throwing a ball, and they throw that ball with their pitching speed, which is 100 miles per hour, and the car's already going 35 miles per hour, okay, if you could allow this motion to go on forever, in other words, air resistance was negligible, gravity is not going to pull the ball down to the ground, pretend like there's no gravity, it's just going through space at 35 miles per hour, and this person throws a ball at 100 miles per hour from the top because that's how fast they can throw, okay? If that actually happens, and you watched it for a whole hour, what you'd see is the front edge of this truck would go a distance of 35 miles in 1 hour. And then you would see this ball go a distance of 100 miles in 1 hour. But that's with respect to the spot on the truck. So what we would conclude is that this ball is actually going 135 miles per hour, because basically this spot on the truck moved 35 miles, and then this spot or this ball moved another 100 miles beyond that. So this ball traveled 135 miles in 1 hour. And that's the fundamental rule. Basically, it says if you have the velocity of, let's say, object A with respect to object C, and you want to know that, that's going to be the velocity of object A with respect to object B. Now I'm going to show you some symmetries here that makes this memorable, plus the velocity of B as seen by C. The main thing is, if you ever want to write this equation, these middle two guys have to match, and these outer two guys have to match these. If you write it that way, you will always have a correct equation. So this says the velocity of the ball with respect to the road, or us, is equal to the velocity of the ball with respect to the truck plus the velocity of the truck with respect to us. So in that case, it's literally saying that the velocity of the ball with respect to the truck is 100 miles per hour, and the velocity of the truck with respect to the road is 35 miles per hour. So you get 135 miles per hour. Now, if the person happened to be throwing it in the negative direction, let's say negative 35 miles per hour, okay, then you'd end up getting negative 35 miles per hour, the velocity of the ball with respect to the truck, plus positive 35 miles per hour, which is the velocity of the truck with respect to the road. So you'd actually get a zero velocity. And that makes sense, right? If you were able to throw it just fast enough for it to counteract the velocity of the truck, then it wouldn't be moving at all with respect to us. It would just fall straight down. Okay. And that's sort of the best case scenario. If you're wanting to escape a kidnapper, or, you know, someone that's got you tied down in the back of a truck, if the truck's going 35, ideally you'd like to run 35 miles per hour backwards and then jump off, and you're less likely to get injured. If you're going 70, you're going to have a bad day jumping off. But if you, like I said, if the truck's going like 30, 20, 15, something like that, you can, you know, try to account for it by making sure you push off the truck so that you're going more of this velocity, which is trying to match the speed of the road. Now you're still going to fall and flip over forward. So if you do it with your back facing the truck, then that could be a problem. Your head would hit and that sort of thing. So this is how we apply physics in everyday life to, you know, worst case scenarios, if you've ever seen that book. So that's what relative frames are about. Relative frames are basically about how does one person see motion compared to what I see motion. And these two are your main equations. That's all you ever need, okay? And it works. In this case, I drew it for vectors, so it works in 1 dimension and 3 dimensions, which is what we're going to cover in the next chapter. All right, so that's enough about reference frames. What I want to do now is I want to give you some examples that we're going to work for this class using the kinematic equations that we just found. I've taken the time to type them up. And the first example is example 1, which technically that stuff we did with the ball and truck, those were some examples, but it's, you know, those are pretty trivial. So look at this problem 1. It says NASA has planned to alter the course of an asteroid that is likely to hit Earth, and does so by putting a rocket in orbit behind the asteroid to slow it down. So if you actually put anything with mass behind something else with mass, then you end up getting a gravitational force pulling towards each other. Well, what that means is if the rocket is behind it, it's going to try to slow down the asteroid over a period of time. So doing that, you'd actually slow down the asteroid, which might not seem like a good idea because it might just still crash the planet. But really what you're doing is you're reducing the basically the orbital distance from the sun for the object that's possibly going to hit Earth. So instead of coming in and hitting the Earth when we happen to be at that particular point in our orbit, it might cross that point in the orbit or cross our orbit before we ever get there, and then end up going closer to the sun instead of farther, instead of the distance from the sun it would have if we didn't screw it up. So that's actually a real life scenario that what we're going to do, or what we could do. For those of you who saw the movie Don't Look Up, that's sort of a scenario like that. Now, what we say is over a period of 2.25 years, the asteroid speed changes from 20.5, notice that's kilometers per second, to 18 kilometers per second. What is the magnitude of its acceleration? Okay, so I've got basically a velocity, which is a final velocity. So I'm just going to label that V or VF. Either of those are acceptable. That's going to be 18.0 kilometers per second. Generally speaking, we work in meters per second. So you can always take a prefix of kilo and just replace that with times 10 to the third. So I'll say 18.0 times 10 to the third. And now I have meters per second. So that's a nice way to think about the system international. Remember, we have the units T dot dot G dot dot capital M dot dot K H capital D, then the base, then deci, centi, milli, dot dot micro, dot dot nano, dot dot pico. So you can say this is times 10 to the 1, times 10 to the 2, times 10 to the 3, 4, 5, times 10 to the 6, 7, 8, times 10 to the 9, 10, 11, times 10 to the 12. That's what all those prefixes mean. And now, well, I'll show you that again in a second when we once I write down the numbers. So I've got the final velocity is 18. I got the initial velocity was 20.5 kilometers per second, which I'm going to write as 20.5 times 10 to the third meters per second. And I also got a time period T equals 2.25 years. Okay. So I've recorded the information. What they want is the actual acceleration. So I'll put A equals question mark by that. Now I'm going to stop sharing. And in so doing, that's going to allow me to let you see my paper. So this is the units things that I wrote down. This is tera, giga, mega, kilo, hecto, deca, DEKA. This is the base unit. So believe it or not, the base unit is actually the kilogram for mass, but you still put gram here. You could also put meter here. You could also put second here. You could put Kelvin here. But all these are prefixes. And like I said, this is 10 to the 1. This is 10 to the 2. This is 10 to the 3, 10 to the 6, 10 to the 9, and 10 to the 12th. These guys, on the other hand, are the same thing, but 10 to the negative. So this would be 10 to the negative 1. Whoa, I wrote 11. 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 6, 10 to the negative 9, and 10 to the negative 12. Okay, they go further on each side, but I very rarely go beyond giga or nano, but just so you'll know. So that's one way of doing it. Also, writing it this way, if you have something in terawatts, for instance, and you want to convert it to kilowatts, you just go 1. Notice I'm counting the moves, not the endpoints. 2, 3, 4, 5, 6, 7, 8, 9 moves. So 9 moves to the right to get from T to K. So if you want to convert something from tera to kilo, say terawatts to kilowatts, you just move the decimal 9 decimal places to the right. Okay. Actually, I think I said, yeah, 9 decimal places. That's right. Okay. If you're going the other way, then you're going to move it to the left. So that's another nice thing to help you. But now back to this. I only covered that because I didn't go over it in the first day of class or the second day of class. And usually we just assume you know it, but I wanted to give you that nice little trick in case you're feeling a little rusty. So now we can calculate our acceleration. We know the definition of average acceleration is v minus v0 over t. Of course, you can also write that as delta v over delta t, or you can also write it as v final minus v initial over t. Those are all equivalent expressions. I just wanted you to be used to them because I'll use them interchangeably. So now what I'm going to do is I want to write 18.0 times 10 to the third meters per second minus 20.5 times 10 to the third meters per second over. Now I've got to convert this to years. What I would like you guys to do is try my pi times 10 to the 7th seconds per year. Try that and tell me what you get. What I did is I actually took the 2.25 years and I multiplied that by 365.25 days per year. 365.25 days per year. And then I multiplied that by 24 hours per day. And then I multiplied that by 3,600 seconds per hour. That's an exact translate. Well, it's pretty exact. It's not exactly 365.25, but that's a fairly exact one. And when I did this, I ended up getting, in fact, 71.0 times 10 to the negative 6, or excuse me, 10 to the 6. Well, definitely not negative 6 times 10 to the 6 seconds. So that's what I did when I did all that proper math. Did anybody take 2.25 and multiply it by pi times 10 to the 7th? Because that is a really wonderful, quick and dirty conversion. It's nice. I just wanted you to see how close it is.
So should we use that conversion, or like with homework, would that be actually wrong?
You're only going to be wrong in the third decimal place. So it's like the real figure is 3.155 and this is 3.141. So you're going to be off if you need it closer than 2 sig figs. But it's always good for approximations and stuff like that. Okay.
So we should use 3.155.
Yeah, if you want to correct it, you can just call it 3.155. That's actually a true value calculation of it.
Okay, great.
Okay.
Gotcha.
Is this
All
one we should have on our formula sheet?
That's one you can have on your formula sheet, the 3.155 or the pi times 10 to the 7th. I don't mind you putting those on there. So now what we have is the time, and I'm going to divide that 18.0 minus 20.5 times 10 to the third. I'm going to divide that by 71.0 times 10 to the 6 meters, or excuse me, seconds. Why do I keep changing the units on this like a goober? So this should just be seconds. When I do that, I end up getting an acceleration of, technically it comes out to be negative 35.21 times 10 to the negative 5th. And that's meters per second per second. Please notice how I wrote that. I wrote meters per second divided by seconds. There's a couple ways you can write it. You can write it as meters per second like that. or you can write it as meters per second per second. The main thing I care about mathematically, it's exactly the same thing as meters per second squared, but the main thing I care about is you calling it meters per second, because I've found that when students think of acceleration that way, they normally get acceleration a little better. What this is suggesting is that this asteroid velocity is going to change by 35.2 times 10 to the negative fifth meters per second each second it travels. So you could literally, like, if you took the 18.0 as the velocity that it has right now, if you subtracted 35.2 times 10 to the negative fifth from that, you'd know that's exactly the velocity it's going to have in 1 second. And if you did it again, you know that would be the velocity in 2 seconds. If you did it again, that'd be velocity in 3 seconds. So that's really the value of that. Now, I asked for the magnitude. If you look back at our question, it says, what is the magnitude of the acceleration? And I said it in triplicate just a few minutes ago. The magnitude of any vector is supposed to be a positive number, just like a length can't be negative. So the acceleration's magnitude is, and what I'm going to do is I'm going to put this in normal standard scientific notation. So if I divide this by 10, this decimal will go over here by a factor of, or by 1 decimal place. But if I divide it by 10, then I need to multiply this by 10. So that's going to be 10 to the negative fifth times 10 to the 1, which would be 10 to the negative fourth. So I'm going to say 3.52 times 10 to the negative 4 meters per second every second. That's the actual answer. Any questions on that?
So like you said, it's always positive.
The magnitude will be yes. And when you get negatives, that's really just indicating for that coordinate direction, it's negative. In other words, it points to the left if you're calling right positive. And by the way, acceleration does not always mean, a negative acceleration does not always mean slowing down. For instance, if you chose your coordinate system such that a car is initially going, let's say 10 miles per hour in the negative X direction, and afterward, after some 2 seconds, it's going 20 miles per hour in that same direction, then what you're going to do is you're going to say final minus initial is negative 20 miles per hour minus 10 miles minus negative 10 miles per hour. That's going to give you, in fact, a negative 10 miles per hour. Divide that by 2 seconds, and you're going to get negative 5 miles per hour per second. But that was actually speeding up. It went from 10 miles per hour to 20 miles per hour. It's just because it was going in the negative direction, the acceleration became negative. So that's one of the key things I want you to understand. Try to work out all the different signs problems that could come up. If both of these are positive and the last velocity is bigger, see whether that's positive. What if the one's positive and one's negative? What if this one's negative and this one's positive? And then what if they're both negative? So think about that a little bit. All right, now let's go to another problem, unless anybody has any questions. You got 70.7 times 10 to the 6th. Was that when did you use the pi times 10 to the 7th, Ariel? Okay, cool. So yeah, it was very close. I said 71.1.0 and you said 70.7. So you see, if you actually rounded that to 2 sig figs and I rounded mine to 2 sig figs, we get exactly the same answer, 71. So the pi is really good to 2 sig figs, which is really back of the envelope type calculations, usually not problems. And to be honest with you, you might even still get the right answers in mastering, but I wouldn't try it because they do take off points each time you get one wrong. All right, so let's share screen and look at our next problem. So we just did number 1. Let's look at number 2. A world record holding jet car is traveling due east at 200 meters per second. When it starts to slow down without turning, that I'm just trying to say it's going in a straight line. It takes the car 22.0 seconds to come to a stop. What is the magnitude and direction of the car's acceleration? So I'm going to write down what I know. What I know is the initial velocity of the car. I'm going to say it's going in the positive direction. So that means east is the positive X direction. So I'm going to say X comma east. on my coordinates. I'll show you what I'm writing on my paper in a second. But now I'm going to say V0 is in fact positive 200.0 meters per second. Now it said it came to a stop. Okay, so that's our way of telling you numbers without saying numbers. And what that means is the final velocity is 0.0 meters per second. And it said it did so in 22.0 seconds. So I'm going to say time is equal to 22.0 seconds. And then finally, it's asking for the acceleration, which they said both the magnitude and direction. So A magnitude equals question mark, and A direction equals question mark. So now that I've explained that, I'm going to let you look at my document again. So what I've done is I have written down the information the problem gave me. That's sort of the key to solving these problems. You got to read them very thoroughly, and then you got to write the stuff down and assign numbers that they give you or infer. Like if I dropped an object, the initial velocity 0, or right here, they're implying, you're inferring, by the way. So if they implied that something came to a stop, you know the final velocity is 0. That's really what they're implying is numerical value. So you write down all those things you know, and then write the things you don't know with the appropriate symbols as well, with the equals and the question mark. So when I work this out, I'm going to say A. Yes, go ahead. Silas?
For initial, is it VI or is that a VO for 0?
You can actually use both. That's why I was trying to stress that here.
Okay.
This, we usually put a 0 there because what we mean is that T equals 0.
Right.
Or sometimes we don't necessarily start at T equals 0. So to get rid of confusion, we'll say V initial and V final. So VI and VO are the same thing. V final and V with no subscript, they're the same thing.
Okay, gotcha. Thank you.
No problem. All right, so now I'm going to just take V minus V0 over T. That's going to be my acceleration. Well, my final velocity is 0.0 meters per second. My initial velocity is 200.0 meters per second. And that's going to take, in fact, 22.0 seconds. And when I do this math, I end up getting 9.091 meters per second every second. And actually, I get a negative on that. Okay. What that means, that negative means that it's actually, in this case, slowing down because we were traveling in the positive direction. So it is actually slowing down. And that also means, hey, in order for me to make this car go from 200 meters per second due east, I would have to apply a force to it due west. Acceleration is sort of abstract, so sometimes students don't really get it that well. So you can always say, let's think about what the force has to be, because force and acceleration, the total force and acceleration have to be parallel. We'll learn that in Newton's laws of motion. But force is something that seems more reasonable. So if you had this jet car moving at 200 meters per second and you wanted to slow it down, you'd have to push a force that way. That happens to be, since the force is this way, that happens to be the same direction as the acceleration. So that's what that negative is telling you. So the acceleration's magnitude is 9 point, notice I had 4 sig figs on the top, 3 sig figs on the bottom. So it's 9.09 meters per second every second is the magnitude. And the direction, since the vehicle was traveling east, anybody want to guess what the direction was?
West.
Yep. So that's what we mean by it. Now you can also do by drawing a coordinate system like I did here. I could have just put in the negative direction, and that would be fair because I did draw, this is the positive direction. Whenever I draw an axis like that, even if it doesn't show both ends, if I show one end with a arrow to it, then you're going to assume that's the positive one. If I draw two, then I have to actually label it. Or I can do like this, which you'll probably learn in engineering as well, like in your statics classes. When I do this, this means I'm calling the right positive up positive, and sometimes I'll even do this, and that all means that the right is positive, the up is positive, and counterclockwise is positive. So any questions on that? Oh, Jacob's trying to get in. That beard that he's got in that picture cracks me up. All right, let's look at example 3 now. So I'm going to share screen again. Scroll down to 3. Now, this is me trying to parse out with you the difference between displacement and distance traveled, which is really the crux of the difference between speed and velocity. So speed is the total distance traveled divided by time. So speed, I'm going to write it over here and you'll see it in a second. Speed is just equal to distance divided by time taken. Okay. Now you can calculate your average speed on a trip to say from Virginia to Florida if you want. And you can do it a couple of ways. You can actually just not even subtract out when you stop to, pee or get a biscuit or whatever. You can just take that total distance and divide it by the total time. And that gives you a good average measure of how long it's going to take you to get to Florida. Because all you have to do then is take the distance to Florida and divide it by that average speed. And that'll tell you basically how long the trip's going to take. However, you could also realize that you're not really moving when you're stopping to get a biscuit or go to the restroom or something like that. So you could cut out those times, and I usually do both in my head, which makes me a horrible driver, but it keeps me from being so bored I don't just run off the road. So, so you could also do it that way, in which case you'd add up the individual distances and then divide it by time. That's another average speed. Generally speaking, all are fair game, but if someone says the average speed over an entire trip, they're usually meaning count those times as well when you weren't moving. Okay. The other thing is velocity is actually displacement divided by time. So this is average speed. I'll put a bar over it. And again, you're going to see this in a second. Average velocity, which I'll put a vector symbol over just to remind you it's a vector, is actually equal to the displacement, which is also a vector quantity, divided by time taken. So in this problem, they're telling you walk 55 meters to the north. So I want to say 55.0 meters north. And then you walk 105 meters south. And that was 55.0 meters, by the way, south. And then you walk 65.0 meters north again. Okay. And later they tell you it took 500 seconds. And that's supposed to be took, not two. Okay, that's all I need. So I'm going to kill this and show you what I wrote down. Notice what they're asking for is what is the magnitude of your displacement, what is the direction of your displacement, and what is your average speed and what is your average velocity. So displacement, which is delta x magnitude, question mark, delta x direction, question mark. And then they're saying, what is your average speed? So S average equals question mark. And then V bar equals question mark. And I think that was it.
Put the paper up a little bit.
Oh, I'm getting ready to pull this up. I just wanted to make sure I got all the information off the page. What is it? Oh, total distance you walked. So total distance. Okay, I'm going to go ahead and kill this and let you look at the screen. I'll let you look at this. So what I did was just wrote down the information that they gave me, which was 55 meters north, 105 meters south, 65.0 meters north again, and took 500.0 seconds. I said that the average speed, the bar over top just means average, is the distance traveled divided by the time taken. The average velocity, I'm notating the V's with vector symbols or arrows over top of them just to remind you that velocity is a vector quantity, but this is an average, and that's just the average displacement, which is what that delta x means over the time taken. Remember, delta x is x final minus x initial, or it's x minus x zero. The main thing is the x vector is a position vector. It points from the origin to where you are at some point in time. What they asked for was the total distance traveled, so I'm going to do that first. Total distance, which by the way is what we mean when we say distance over here. So the total distance is going to be 55.0 plus 105. That looks to me like 160.0 plus 65. That gives me 225.0. So that's one of the answers. Does everybody agree with my crazy arithmetic? Because I'm doing it in my head and your instructor's just not that bright. So, all right. The delta X, the magnitude. So the delta X vector is supposed to be X minus X initial. Okay, that works. It could also be called, like I told you before, X final minus X initial. Either one of those are acceptable. Like I said, the I is interchangeable with the 0, and the F is interchangeable with nothing. So what we can do now is calculate what this is. Well, what we want to do is create a coordinate system. I think this is the cleanest way of doing it. Okay, and I did have to make up some crazy stuff for this problem. I had to imagine that the door to the house was directly in front of the back door to the house, and there's like no walls in the way. So there are some old house designs like that, but that is an oddity. So what happened was we first walked 55 meters to here, and then we walked 105 meters back to here. So this distance is 105. This distance was 55.0. But notice that 105 is not the coordinate there. What I basically did was I walked 55 and then walked back 105. The difference between those two is exactly 60 meters, if I recall my arithmetic. Excuse me, 50 meters. That's why you don't recall your arithmetic, because there's a good chance you're going to forget it, and it's better to just do it again. So we're back to negative 50 meter. We're back to negative 50.0 meters. And then we walk an additional 65. Which puts us at 15.0 meters. Does that make sense to everyone? 55, then if I take 55 minus 105, I get negative 50. And then if I take negative 50 plus 65, calling the north direction positive, I get 15 meters. So my displacement is in fact 15.0 meters minus 0 meters, which is just 15.0 meters. That's the magnitude. Now, technically, just having the sign being positive there in one dimension, I'm actually giving you the direction as well. But that's why I use the words like north and south. So the fact is, I ended up coming back, still going north of the house, because I ended up on this side. If I'd gone instead of 65 meters, maybe I'd only gone 45 meters, then my final position would be south of where I started. But in this case, I'm north of where I started, which was right here at the front door. So the direction is north. Does that make sense to everyone?
So when you say direction for something, it's always like at the end of it.
Yeah, you normally would say 15 meters north of east, 15 meters, 15 degrees north of east, or something like that.
Okay.
Okay. Now what we're going to do, someone, and yes, that looks like what I got to regarding your figure, Zach, or Zachary. So the next thing we want to do is find out what the average speed is. Well, average speed is equal to 225.0 meters divided by 500.0 seconds. So we get like 4 sig figs. When I actually do that math and I divide 225 meters by 500 seconds, I get 0.4500 meters per second. And that's my average speed. Again, average speed is just total distance traveled divided by time taken. And that counts your stops and turns arounds and all that stuff, unless you specify otherwise. Okay. Now, the last part is the average velocity. I think that's the last part. Yeah, average velocity. So the average velocity, and by that, it's a vector quantity. So I really need to do magnitude and direction. We've already figured out the direction of the displacement. So clearly the velocity has the same magnitude. I can put the vector symbols over there to remind us that. But V average would equal delta X, which is 15.0 meters divided by 500.0 seconds. And that's a god awfully small velocity. In fact, it turns out to be V average is actually equal to 0.0300 meters per second. And that's the magnitude. And you could say, if you just want to write the vector average like this, you could just say 0.0300 meters per second north. That would give me the magnitude and direction. Or I could separately say DIR for direction is equal to north. Any questions on that? All right, so let's look at another example since we're moving right along and it seems like y'all are getting this stuff. That was example 3. Example 4, a runner completes the first 2 laps of a 1600 meter race with an average speed of 6.25 meters per second. If the runner wishes to average 6.667 meters per second, which by the way happens to be a 4-minute mile, I'm just giving you that for context. So don't use that to help solve the problem, even though that helps. It could actually make the problem a lot easier. I'm not wanting you to use that. I just wanted you to let you know that's a 4-minute mile, which was like a really big deal when I think Bannister did that in Eugene, Oregon, broke a 4-minute mile. So what we're asking now is what average speed must she complete the last 2 laps with? Okay, so that's a neat problem. It really relates to how we use average speed in calculations and whatnot. So I thought that would be a good example to work. So let's look at example 4. Okay, the information I have is I want the total average, or actually I should say speed. I'll say I want the total average to be 6.667 meters per second. What I found was that the first 2 laps, which is the first half, so the S first half average was in fact 6.250. So first half means 800 meters. And you can treat that to any number of decimal places. Since it's supposed to be a race and that sort of thing. If the runner wishes to do that, what we want to know is the S average for the second half. So that's really what we're looking for. So I've gotten all the information now that I need. I'm going to stop sharing and show you what I wrote down. So what I wrote down was the total average that the person wants is the 6.667 meters per second average. And that, by the way, is 1600 meters, which is essentially a mile. And then the first half, in other words, the first 2 laps, which was 800 meters, they had an average of 6.25 meters per second. So what I know is S total should be the total distance divided by the total time. I know the total distance is 1600, but the total time, obviously, because I gave you that hint, it should be 4 minutes. So you could work out a lot of stuff easily, but we're going to pretend we don't know that. Okay. What I'm going to do now is figure out, well, how long did this take? And then, of course, how long will the rest need to take to make this average? So first thing I'm going to do is I realize that S equals D over T, so that I can find time is equal to distance divided by speed. So what that means is T for the first half is equal to 800.0 meters. Again, any number of decimal places for that, divided by 6.250 meters per second. When I do that, I end up getting, I think I worked this number out already. Yes, 128.0 seconds. Carrying an extra sig fig. Okay, so that's how long the first half of the race took. In other words, the person finished 128 seconds. Notice, by the way, that's basically 2 minutes and 8 seconds. A 4-minute mile, if you're going to average it through the whole race, it should have taken you exactly 2 minutes. So they're 8 seconds behind the pace, basically. So you know you got to speed up. And you knew that already because 6.25 is less than 6.667. So that's the time for that. Now, what I also know is that the time for the total is equal to the distance total over the average speed total. Okay, so I'm going to take the 1600.0, again, any number of decimal places is acceptable there, sort of. And then I'm going to divide that by 6.667 meters per second. And when I do that, that's going to give me the time the whole race should take. And in fact, what you get is the time the whole race should take is 239.988 meters, or excuse me, seconds. So notice if it was actually 4 minutes, that'd be 4 times 60, that's 240. So this is very close to the 4 minutes I suggested. And in fact, I only have 1, 2, 3, 4 sig figs. So really these are extras. Okay, so that's the total amount of time. However, I've already used 128 of that. So I need to now compute the average that's necessary. And the average that's necessary uses only the remaining seconds. So T for the second half must be equal to T total minus T to the first half. Does that make sense to everyone? It's a little convoluted thinking through this, but this is, I mean, that's sort of the nature of it. You got to think through things in a college level science course, and that's what we're doing. So I'm going to take 239.988, again, 2 extra sig figs there, seconds, minus 128.00 seconds. Okay, and that one actually has only 1 extra sig fig. And that's going to give me the actual time. The actual time I have left is, in fact, I'm going to type it out, 239.988 minus 128 equals 111.988. Seconds. Again, these are extra digits. So now I can say that the second half average is going to equal 800.0 meters divided by that time, which is 111.988 seconds.
Professor, I got something else for the time. I got 111.8806.
That sounds close enough. It's probably just where you might have rounded a little earlier than I did in something, but yeah, that's plenty close.
Okay.
So in order for them to catch up, back up to the 4-minute pace, the average speed is going to have to be 7.143 meters per second. Actually 144 meters per second with proper rounding. Okay, so that's a typical problem that we solve in physics as well. Does that make sense to anyone, to everyone? Does anybody have any questions or problems they don't understand about that?
And you wrote the subscript was those time for the second half?
Yes, this was the amount of time that the second half had to take.
Okay. Oh, but that's, sorry, the answer is speed. for the
Yes,
second.
yes, meters per second, yes.
Okay, gotcha.
So let me recap, because this is a big problem where you had to do a lot of things. So what we were told was the total average that the person wanted. And I suggested that's like a 4-minute mile, which is pretty damn hard. I got down to an 8-minute mile, but that was about as fast as I could ever get it. But you know, I wasn't fat then, at least, but I was heavy because I'd lifted a lot of weights. What we know is the first half of the race, they averaged 6.250 meters per second, which is, you know, well below the 6.667 pace. So you know already you got to speed up. So what they're asking you is what speed in the second half am I going to have to average to get back to that? So what we first had to do was say, well, how much time did we use up in the first half? Well, the time for the first half is just the distance in the first half, which is 800 meters, divided by the average speed in the first half, which is 6.25. So I got 128 seconds. But I said, okay, well, if I want to average 6.667, how much total time do I have to run the race? So that could have been a whole different question to ask you, as could how much time do you have to finish the last 2 laps? That could have been another question I could have asked you. So this could have had like 4 or 5 different parts. But to figure out the total time I had, I took T total and solved for that by taking the total distance, which is 1,600 meters, and dividing it by the average speed that we wanted, which was 6.667. And I may have had polio when I wrote that particular S. I don't know why it looks so bad, but anyways. So if I divide that 1,600 by 6.667, I got 239.988. I really should have just called that 240. It would have been easy enough. But that tells me the total time has to be 240. I've already used 128. So that allowed me to actually get the time I had for the last leg of the race. And I already know the distance for the last leg of the race. It has to be 800 meters. So all I have to do really is find the 800 meters and the time taken. Well, I take the 240 minus 128. That gives me how much time I got left. Divide 800 by that. That gives me the average speed that I need at the end. Any questions? Okay. It looks like y'all are getting that. I hope it wasn't too brutal. All right, let's try example 5 now. A goofy physics instructor is on top of a 3-story, 30.0 meter high building doing a gravity demonstration when he absentmindedly steps off of the building, luckily with no speed. How long will it take his students to hear the gelatinous crack of his landing? I'm picturing the sound of fat and meat and bones hitting the ground, and it made me laugh, so I wrote gelatinous crack. And that then made me laugh again. So, and how fast will he be going when he hits the ground? So what I'm writing here is that my initial height, you could use X or Y here. Let's go ahead and use Y just to change up things, so you don't get used to always using the same symbols. I'm going to say Y initial is 30.0 meters. So that's what that 30 meters is I would call that initial position, 30.0. I'm also given that I luckily fell with no speed. So that tells me that my V0 is equal to 0 meters per second. And what I want to know is how long is it going to take? So I'll put question mark by that. And how fast will I be going? So I'll put a question mark by that as well. I've now got all the information I need. I'm going to stop sharing. And you can see what I wrote down was, in fact, exactly the figures I suggested. So now I can slide this up here and we can start working this problem. So by calling the initial height 30 meters, I've actually forced myself into a coordinate system basically. So here is my 30-meter building. 30-meter building. I'm going to say this is my y-axis and this is my x-axis. By doing that, I've already defined the up direction as positive, and now I can say that the acceleration then is negative g, which is negative 9.80 meters per second every second. Okay, so now I need an equation that relates the final velocity to a, or let's do the first one. The final velocity or the time to the initial velocity y and the acceleration. So one of your equations is y is equal to 1/2 at squared plus v 0t plus y0. And that one allows me to solve for time if I have the y, the a, and the initial velocity and the initial position. So yeah, this works perfectly. So I'm going to use that one. So I'm going to say y equals 0 meters is equal to 1/2 negative 9.80 meters per second times t squared plus 0 plus my initial position is actually 30.0 meters. So what I get is 0 is equal to negative 19.6 meters per second t squared plus 30.0 meters. So that looks like it might be difficult, but it's actually quite easy. I just pull this to the side. I'll say 19.6 meters per second t squared is equal to 30.0 meters. So t is just going to be the square root of 30.0 meters over, there's a 1 there, 19.6 meters per second, which this is where it comes in handy realizing that's meters per second squared, because the meters are going to cancel out and the second squared is going to come to the top, and you take the square root of second squared and you just get seconds. So with this case, I get that it's going to take me 1.237 seconds to hit the ground. That 7's an extra sig fig. I usually underline the extra sig figs that I add just so y'all can keep track. I don't generally care about sig figs on homeworks and tests if you actually have to do the writing as opposed to multiple choice. Now, the other part of the question is what the final velocity is. Well, I could actually use this figure, but if I made a mistake to calculate this, then I would have 2 wrong answers, and the instructor might not be caring enough to check that I did it right or wrong, and therefore wouldn't give me partial credit. So it's best to just use the initial values that you had, okay, instead of the things you calculated. So if I could find something that related initial velocity, final velocity, initial position, final position, and acceleration, that would be best. Well, that equation is v squared is equal to v0 squared plus 2a. Let's do y minus y0 since we're in the y world right now. Okay. My initial velocity, of course, is 0. My final velocity is what I want to know. My a I know, and my y initial is 30 meters. And this is 0 meters. So what I have is v is equal to the square root of 0 squared plus 2. Now this might be scary for a second. Look, I got 2 times negative 9.80 meters per second. But look what comes to save us. 0 meters minus 30 meters is negative 30.0 meters. So I end up getting a positive under the square root. And when I do that, I end up having 24.248 meters per second. Notice technically you would have to do a plus or minus here. That's the nature of this being a non-vector equation. It doesn't give you information about the direction. You guys know the direction is downward, which is what we call the negative direction. So if we really wanted to say the direction, we just would have had to force a negative on there. Whereas if I used v equals v0 plus at, that would have given me the right sign, but I would have had to use t to get there. Okay. And this actually has 2 sig figs too many. So I'm going to say it's basically 24.2 meters per second is how fast you hit the ground. By the way, that's like 54 miles per hour. So that's a painful deal. You don't want to hit the ground that fast. Okay. All right, let's look at another example because we only got like 7 minutes left.
Real
Yes.
quick, Professor.
Go for it.
I couldn't get the equations for the time and for the other one, the velocity. Well, like
Right.
it says y 1/2 at squared. Could you sound those out?
Yes, y equals 1/2 at squared plus v sub 0 times t plus y sub 0.
Okay.
Okay,
And the second one for velocity.
that was v squared, which is final velocity squared, equals v sub 0 squared plus 2 times a times parentheses y minus y0, close parentheses.
Thank you.
No problem. Yeah, make sure you guys stop me if I'm going too fast too. I mean, y'all pay me the big bucks, so yeah, y'all deserve to have my attention. So let's do example set 6 now. And share the screen, yada yada. All right, so from the edge of a 100-meter cliff, a ball is thrown straight upward with a speed of 24.9 meters per second. So I'm going to write 100.0 meters high cliff because I haven't really decided what my coordinate system will be yet. I'm going to say my initial speed or my initial velocity is 29.4 meters per second up. Again, I'm not saying a sign on that because I haven't decided my coordinate system. And I want to know how long it'll take to reach max height. So T max is question mark. How high will it be above the cliff surface? So Y max is another question mark. And if on its way down, it misses the cliff and lands at the bottom of the cliff, how fast will it be going? So I'll say V bottom is equal to question mark. And how long was it in the air? I'll say T hang time. Question mark. Okay. Hang time like in college and NFL football when they punt. Okay. So really that's how long it's aloft. So now that I've got that information, I'm going to go back, show you what I wrote down. So I'm going to draw a little figure to make sense of what coordinate system I'm going to use. And what we're saying is the ball was initially shot up from this height right here, which is 100.0 meters above the bottom of the cliff. In other words, the bottom of that, whatever it is, ravine or something. Okay. So the ball is actually going to go up, reach some max height, and then come all the way down like that. What I think I'll do is I think I will call this the x-axis, and then I will call this the y-axis, and then this is the origin. So with that in mind, what I have is the initial height of the ball is actually 100.0 meters. Now you could have put the origin up here, and I suggest you do that and solve it and see if you don't get the same answers. But I'm going to say y0 is 100.0 meters. I'm going to say v0, since it's pointing up, is in fact positive 29.4 meters per second. And I know now that A is have to be negative because the Earth's gravity pulls things downward. So it's going to be pointing in the negative y direction. So I'll say negative 9.80 meters per second. And let's calculate T max. So what I know is that V is equal to V0 plus AT. That's an accurate equation when the acceleration is a constant. If we ignore air resistance, the acceleration of gravity is a constant, right? The acceleration of gravity is more or less a constant for, up to around a couple hundred meters above the Earth's surface. It starts to decrease then, but it's essentially pretty good to treat it as a constant. Air resistance would actually add something to make the acceleration non-constant, but we're ignoring that. So if I do this, I realize that when the ball reaches a max height, V max is actually 0. That's the key to understanding this. Because if it still had any more velocity upward, it would have went higher up. Or if it had a velocity downward, then it must have came from somewhere where it was already stopped. So the max height always has to have the velocity equal 0. So I'm going to say 0 is equal to 29.4 meters per second minus 9.80 meters per second times time. So you can see time is just going to be 29.4 meters per second over 9.80 meters per second, which gives me exactly 3.00 seconds. In fact, that's why I chose that particular velocity. Was because it was 3 times g. Okay, so I got that first part. Check. Now what I want to know is what is that max height? Well, I need an equation that gives me position or distance I have a final velocity, I have an acceleration, I have initial velocity. So I'm thinking v squared equals v0 squared plus 2a y minus y0. Notice I'm using y again just because I happen to coordinate it along the y-axis. I could have used the x-axis. It doesn't matter. Like I said, these symbols are just symbols. So what I'm going to do now is calculate the initial position was in fact 100 meters. And this is y max. So that's the thing I'm actually solving for, is that y. So I'll get 0 squared is equal to 29.4 meters per second squared plus 2 times negative 9.80 meters per second times y max minus 100.0 meters. By using that coordinate system, this answer would have gave me like a god awful number if I put 0 here. It would have given me, you know, basically 100 meters taller than what it really reached. So what I'm going to do is solve for y max, and basically what that entails is I'll pull this over to this side, 29.4 squared, by the way. .4 squared is 864.36. So I've got 864.36 meters squared per second squared is equal to, now I wrote it over here again, but really I've switched them. So this is going to be a positive now. So this is 19.6 meters per second times y max minus 19.6. Actually, we can do this even better. I can go ahead and multiply that by the negative, and I'll get 1960 meters squared per second squared for this guy. And now I just have to add this to this side and divide by 196. So I'm going to do 864 plus so I get 2,824.36, 2,824. And that's going to be meters squared per second squared is equal to 19.6 y max. And that 19.6, of course, has units of meters per second. So y max is just going to give me 144.0 meters. Actually, that should be 44 point. It's actually 0.1. Maybe it was 144. Anybody else get the same answer I did?
Could you move the page down?
Oh, yes, thank you. That might help, huh? Oh, that wind's super helpful. Yes, I guess that's right. Well, if it was actually traveling exactly 29.4, and I did that for 3 seconds, I would expect it to go 88.2. So no, it's definitely got to be like the 44.1. I don't know how I ended up getting that extra. The y0 was 100. So the y max should actually come up to be, oh, okay, yeah. Gotcha. So remember, that's y max, that's relative to the origin down here. So that means when I ask for the y max above cliff, that's 44.1 meters above the cliff surface. Okay, that's key. I forgot when I'd worked this problem earlier, I got the same numbers, but I got 44.1, but I forgot I'd used the coordinate system origin being up here. So that answer gave me exactly 44.1. So that's how I corrected for that. I've now done Y max. If you want to find out what the velocity at the bottom is, we've already ran out of time. Crap. Let me go ahead and give you the answers to this so y'all can try to work it out. The answers to this, because I've already worked it. This is number 6. The V at the bottom turned out to be 53.1 meters per second. And the total time on the air turned out to be 8.4229 seconds. That's way more sig figs than necessary. And I found that, yeah, that's right. And by the way, if you just dropped it from that height, the height would be, or the velocity would have been 44.3. So that's considerably smaller. For number 7, let me give you these answers as well. For number 7, I got 53.1 meters per second. So basically the only difference is for number 7, if we look back at that problem, let me share it real quick for you. Number 7 says, imagine throwing the ball downward from the same cliff in example 6. The initial speed is again 29.4 meters per second. How fast will it be traveling when it hits the ground? I didn't work out how long it'll be in the air. I was going to do that on the fly. But anyways, notice that it didn't matter if you threw it up at 29.4 or down at 29.4, it still hits the ground with the exact same speed, 53.1. Okay. How long it'll be is way less than, the amount of time it was in the air last time. So you can just do the time in the air would just be x equals x0 or y0 equals 100, y equals 0. And then you use 1/2 AT squared plus V0T, that equation to solve for it. Sorry, I ran out of time, folks, but that does complete chapter 20, chapter 2. You can see a lot more examples on the YouTube channel. I did some with the aircraft carrier. I did some with jets taking off. I did some with the Tesla that has such an amazing acceleration. So you can see a lot of problems using these examples. I've got a car chase problem in there where a police officer sees somebody speeding and has to turn around and then try to catch them. So there's a lot of good problems in there on my YouTube channel. So check those out. We finished with chapter 2 now, and we'll start chapter 3 next time. You guys are free to go. If you have any questions, stick around, but I only got about 4 minutes. So Silas, you have your question, sir?
Yeah. One of the biggest problems for me with the homework was that it was so difficult to get estimates. Like you said, we shouldn't be looking anything up, but things like one of the questions was, well, they only gave us like the diameter of the moon, and we were supposed to find how much larger the surface area of the Earth was. So like, will we have to look up the surface area and stuff of the Earth?
Well, what they're sort of expecting is that you probably know that the Earth's radius is about 4 times the moon's radius, and then you can get it from that. But if you didn't know that yet, you'd have to look it up.
Yeah, okay. And then there was one about hold on. There were a lot of estimates, like with, for example, the entire population of the US forming a human chain. Like there's no way we would know like the average US arm span and like all those things, right? Like we would have to look those up.
You have to make some assumptions. Like I would assume there's about 370 million people on the United States. I would say the average person is probably, because we're counting a lot of kids right now, I would say maybe the average person is 5 feet tall. Maybe you go ahead and just say their arm span is 2 meters. That's a pretty good estimate.
So like, but essentially you have to estimate a lot. And like, I guess my question is like, will we have to do that on a test? Because that's so many estimations. Like, I feel like it wouldn't.
Yeah, when you do that, if you're off by a factor of more than 10, then you've done it wrong. If you're off by a factor of 100 or, again, more than 10, like a 10.5 or something like that, you're probably wrong. But if you're, being fairly like using 6 meters instead of 1 meter, then you're probably not going to be off by, much more than a factor of 2. So it should actually work out. So don't stress out too much about that. The biggest thing when you go to start doing those estimate ones is normally I would have you write that out and then I'd look it over. But the good news is your practice tests have a lot of the estimation problems in them. So the more you do that, the more you'll see the right answers for what they do, and you'll probably get them all right anyways. And I very seldom make up new problems regarding estimation. The only things I've normally made up is, how many marbles can fit in a room, or how many house flies can fit in a room, stuff like that. So don't worry too much about those problems. I'm not going to be unfair to you, trust me.
Okay. And then my last one was for one of the earlier questions. We were converting, I think it was liters to gallons, and I tried finding a conversion in the book, and it was that a gallon was 1/4 of a liter. But then when I applied that, it didn't work. It was like the wrong conversion. So like,
Yeah,
will
it's a
you give
little
us
bit off.
conversion?
There's another conversion. You can go from gallons, which is 128 ounces, and then you can go from ounces to liters or milliliters. That's a little bit more surefire way. I think I don't think it's gallons exactly 4 liters. A gallon's 4 quarts, but a quart and a liter are slightly different.
Yeah, exactly. So like with stuff like that, will we get that conversion so that it's right according to what you would want?
Yes, yes, or you have the table in the front of your book.
Okay,
like
but I've tried
I'll-
looking in the book because it's
yeah.
virtual. I couldn't find that table.
Yeah, that's kind of a weird thing. Let me make a copy of those pages and I'll post them online. So that'll be something else you can print out or whatever if you want.
All right. Yeah, that'll be great. Thank you so much.
No problem. Is that it?
And yeah,
Silas?
that's it.
All right.
Yeah, that'll be it.
Anybody else? I only got
Yeah, I
like,
had a question.
go for it, Eileen.
So I realized that the dates on Canvas are different than the ones on, what is it called? The physics
Limited Mastery?
online. Yeah. I realized that kind of too late. So do you want us to go off the one online on the mastering part instead of the one that's on the gradebook?
Okay, so in our first day, I told y'all those dates were the day that we start chapters. So when I have chapter 21 or chapter 8 or chapter 2 or something, that's just the day I start that chapter. That has nothing to do with the homework. So what I advise everybody to do is go and copy the chapter date, the dates for all the homeworks into your calendar so you don't miss those. I'm not doing anybody, the only people I'm giving extensions on their late homeworks are people that started the course late, like they registered, 2 or 3 or 4 days late. So you don't worry, we've got a ton of homeworks and we've got a lot of extra credit chances. So, having a 1 grade be marked a little bit because you're late, it's not going to kill you.
Okay, no, I was just asking about it.
Okay.
I'm just a little bit overloaded. Thank you.
Yeah. Don't freak out. It's plus I end up dropping so many, you'll be fine. Anybody else? All right, I gotta go, folks. Feel free to email me or even text me with other questions since I didn't have much time afterwards. See you guys.